Alright, so in this video I'm going to be explaining another important article with the title Domain Generalization with Adversarial Feature Learning. This paper in 2018. So we tackle the problem of domain generalization, how to learn a generalized feature representation for an unseen target domain by taking the advantage of multiple seen source domain data. We present a novel framework based on adversarial autoencoders to learn a generalized latent feature representation across domains for domain generalization. To be specific, we extend adversarial autoencoders by imposing the maximum mean discrepancy measure to align the distribution among different domains and matching the aligned distribution to an arbitrary prior distribution via adversarial feature learning. In this way, the learned feature representation is supposed to be universal to the seen source domains because of these maximum mean discrepancy regularization, and is expected to generalize well on the target domain because of the introduction of prior distribution. So you see this object recognition as multi-source domain generalization. Given labeled data sample from several domains, domain generalization aims to extract universal knowledge across seen domains to learn a classifier to be used in previously unseen, or we say target domain. This is an unseen target domain. So we are classifying and we have a classifier training and we get that. So a basic assumption is that there exists a feature space underlying the seen multiple source domain and unseen target domain on which a prediction model learned with training data from the seen source domain can generalize well on the unseen target domain. Such a feature space for domain generalization is expected to have these properties. First, the feature space should be domain invariant in terms of data distribution. This is because the feature space, all the map labeled data from the source domain are used to train a prediction model for the unseen target domain. If the data distributions of different domains in the feature space are still different, the generalization of the prediction model would be poor for a target domain. The second property is that the feature space should capture discriminative information to class labels, which would be helpful to learn a precise prediction model for a target domain. To enable the learned feature space to have the first aforementioned property, we extend this model in this reference, which is a recently proposed probabilistic autoencoder, to the multi-domain setting for learning cross-domain invariant features using MMT in an adversarial learning manner. So, adversarial autoencoder is in this paper is a probabilistic autoencoder. There are many kinds of autoencoder: variational autoencoder, variational graph autoencoder, adversarial autoencoder. There are many types of autoencoders. So it's a probabilistic autoencoder which aims to perform variational inference by matching the graph, the aggregated posterior for the hidden codes, with an arbitrary prior distribution using an adversarial training procedure. So let X be input, this X is input, H be the hidden code of the autoencoder. So Q H condition on X and Q of X condition on H an encoding distribution and a decoding respectively. So it's classic autoencoder. Then the aggregated posterior can be computed, where P is a marginal distribution. Let P of H be the prior distribution one wants to impose on the codes. And so this reference 23 borrows the idea of GAN to minimize the reconstruction error for the autoencoder, and meanwhile guide Q to match P through attaching an adversarial network on top of the hidden codes of the autoencoder. So this is the overview. We first extract features, either handcrafted feature or deep learning based feature based on the given image. Next, we perform domain generalization by aligning the distribution of hidden representation based on MMD and match the hidden representation with Laplace prior, because you see this Laplace prior. We want to be similar to that with an adversarial subnetwork. So we have discriminator and we have classifier. So we have an encoder Q to map inputs to hidden codes and a decoder P to recover inputs from hidden codes. The pair of encoder and decoder are shared by all domains, including the target domain in the prediction phase. The reconstruction error of the autoencoder over all the scene source domains is this one. This is the reconstruction error. To make hidden codes invariant underlying the scene source domains, we introduce MMD-based regularization. The form of R is specified in section 3. Though the MMD-based regularization term can help learning hidden codes projected onto which the difference among the source domains could be reduced, there is a risk that the invariant hidden codes are overfitted. Even in model editing, there is a risk that you are overfitting. So, motivated by this model, we impose a prior distribution. So even in model editing, we can have a prior distribution, and we have that. We reduce the KL divergence in that case. But here, we impose a prior distribution to regularize the learned hidden codes by matching Q to P through designing an adversarial network. Here, generator of the adversarial network is the encoder of the autoencoder. So following GAN, MMD AAE can be written as the following minimax optimization problem. So it's classic GAN. Classic GAN plus MMD plus autoencoder. And then we do it for multi-domain MMD-based regularization. I have a playlist for reproducing kernel Hilbert space. So we are minimizing the distance between domain L and T can be measured because they have their mean as well. So everything is here. We have this autoencoder, the MMD loss. So for each domain, we give it to the feature extractor. And then autoencoder here, and then we have discriminator. So we have GANs plus autoencoder plus classification. 3 losses. The rest of that is just theoretical things to support their claim. So once they get the inputs, we go through a loop. We sample mini batches from the sample H from the Laplace distribution. We need this because we have a prior distribution to make sure that we are not overfitting, as I said. Then we compute the gradient take gradient up to maximum objective. So to minimize that loss, the total loss, we do this. You have adversarial network, and that's it.